Topic: solubility. Solubility and Henry's law. Class 12. Subject: chemistry. Chapter: solution. Hello students. In our previous video, I discussed concentration terms like molarity, molality, and mole fraction. Those were mathematical tools. Now today's discussion is very important because we move one step ahead from concentration to equilibrium behavior. Today we will study solubility effect of temperature, solubility of gas, and Henry's law. And at last, important numerical problems. Let us begin. Number 1, solubility of solid in liquid. Solubility of solid in liquid. What is solubility? If this question is asked, what is solubility? Then we shall write the answer in this way. In a saturated solution, at a constant temperature, the amount of a solute that dissolved in 100 gram of a particular solvent, maybe water, For example, water. Is called solubility. Solubility. Take an example. At 25 degrees Celsius, solubility of table salt in water is 35.7 gram per 100 gram of water. It means in 100 gram of water is one of the solvent, table salt or NaCl, dissolved at 25 degrees Celsius, maximum up to 35.7 gram. This is the solubility. In another way, I can say it: to prepare a saturated solution at 25 degrees Celsius in 100 gram of water, 35.7 gram of NaCl dissolved. This is the solubility of NaCl. We should consider two important points regarding this. So, here I am writing notes. Number one, solubility of a solute, changes with change of nature of solvent. Nature of solvent. It means same NaCl has different solubility in water and in alcohol at same temperature. So with the change of nature of solvent, the solubility of a solid changes. Point number two, solubility occurs under dynamic equilibrium. Solid NaCl get dissolved into solvent, that means dissolved particles, and since solution is saturated, that means reaction is reversible, and the rate of dissolution and precipitation are in equilibrium. This is dissolution, and it is precipitation. And the two rates are equal. The rate of forward reaction is equal to rate of backward reaction. Let us discuss point number two. types of solid solutes. Type of solid solutes. Number one, solid that number one, solid that dissolve with absorption of heat. That means if solubility is endothermic, then solubility increases with increase of temperature. If the solubility is endothermic, then solubility increases with increase of temperature. For example, KNO3 in water. Number two, solid that dissolves with release of heat. That means if the solubility process is exothermic, in that case solubility decreases with increase of temperature. Example for this case is solubility of CaOH2 in water. Now there is a question: why solubility changes with temperature? Answer is on the basis of Le Chatelier principle. The solubility follows Le Chatelier principle. That means if dissolution, let us take equilibrium equation, solid dissolved particle, if the process is endothermic, that means during in endothermic process, increasing temperature increases solubility. Increasing temperature increases solubility. And the reverse is true for exothermic process. Increasing temperature decreases solubility. Now let us look at the graph. Here I am trying to write the graph of solubility versus temperature. This graph will give you lots of informations. Here I am writing grams of solute per 100 gram of water. In this way, and here it is 0. The value increases 10, 20, 30, 40, 50, 60, 70, etc. And here is temperature, increase of temperature from left to right, 10, 20, 30, 40, 50, 60. And in some cases, just take one example of potassium nitrate. Potassium nitrate, in case of potassium nitrate, the curve goes like this, a steep upward, KNO3. Just take another example, that is ammonia. It comes in this way. Here it is case of NH3 gas, ammonia. Take another example, sodium nitrate. sodium nitrate, it goes like this. NaNO3. Step. If you are taking the example of sodium chloride, it is like almost constant NaCl. If we take one more gas, that is sodium sulfur trioxide, the graph will be like this: sulfur trioxide, and so on. What are the important observation of this graph? Observations. Number one, most solid solubility curve slope upward. Solubility of most of the solid curve curves slope upward. Number two, some solute gases slope downward. Number three, steeper curve, greater temperature effect. So, greater temperature effect. And last one, if two curves intersect each other at that temperature, both have same solubility. Both have same solubility. These are the observations. Just watch the graph. You will find most important observations. Most solute curve slope upwards. Some, at least gases, slope goes downward. Steeper the curve shows greater the effect of temperature. And at last, if two curves intersect each other at that temperature, both the solute have same solubility. These are the observation. Let us discuss point number 3, that is solubility of gases in liquid. Here there is interesting thing. The chemical structure of the solute and solvent dictate the types of force possible and consequently are important factors in determining the solubility of gas in liquid. For example, just I am repeating once again, the chemical structure of solute, that means gas solutes, and solvent, suppose solvent is water, dictate the types of forces possible and consequently are important factors determining the solubility. For example, under similar condition, solubility of oxygen in water is approximately 3 times greater than that of helium. But 100 times less than solubility of CHCl3. That is chloroform. Why? Because the polarity in chloroform is far more than that in oxygen, which is slightly higher than that in helium. So the nature and the structure of solute and solvent affect the solubility. Considering the role of solvent structure, solubility of oxygen in liquid hydrocarbon. Take another example. Considering the role of a structure of solvent solubility of oxygen in liquid hydrocarbon such as hexane, C6H14 is approximately 20 times greater than that in water. Water. Now, effect of temperature. Let us consider the factors affecting solubility. Factors affecting solubility of gas in liquid. Very first, effect of temperature. The matter can be explained on the basis of graph. Here I am expressing the graph solubility of gas it is mole per liter. Mole per liter. And here is temperature. Zero, 10, 20, 30, etc. You will find in all cases graph goes like this. It is methane. Here is oxygen. Here is carbon monoxide. Here is nitrogen, and so on. In every case, you will find with increase in temperature, there is decrease in solubility. When temperature increases, solubility of gas decreases. That is why cold drink, stored in a refrigerator, and fish die in warm water. Let us discuss point number 2, effect of pressure. Solubility of a gas increases with increasing pressure. With increasing pressure. Now comes to Henry law. let us discuss Henry law, which is one of the most important law for examination. What is a statement? Statement of law is at constant temperature the solubility of a gas in a liquid is directly proportional to the partial pressure of gas over or above the liquid surface. Above the liquid. This is the statement. Mathematically, Henry law may be expressed in two different formula. One, partial pressure of gas over the liquid is directly proportional to solubility, that means mole fraction, or this equation may be written as partial pressure is equal to kH into x. X is where P is partial pressure of gas, XH, KH is Henry constant, and X is mole fraction of solute, that means gas in solution. Henry law will also be expressed in another way, and that is C equal to K into P. This is another expression. Here C is concentration, P is partial pressure, and K is constant, that is Henry constant. So from equation 1 we shall discuss the characteristics of KH. Characteristic of KH, that is Henry law constant. Here point 1 is if partial pressure is kept constant, then from equation we may write X directly proportional to 1 by KH. That means solubility decreases with increasing constant. It means higher the value of Henry constant, the lower is solubility of a gas in liquid. This is one of the observation. Second, a smaller the value of KH, higher is solubility of gas. Take fifth point. Now, application of Henry law. Application of Henry law. In case of cold drinks, what happens? Carbonated drinks contain carbon dioxide dissolved under high pressure. When bottle is opened, pressure released, and CO2 gas escape with bubbling. This is the Henry law action. Similarly, we can consider one more example. Number 2, let us consider the case of scuba divers. Scuba diving what happens? Diver goes deep under sea water where pressure is very high. Nitrogen dissolved more in blood due to high pressure. If diver suddenly comes up, pressure decreased, nitrogen bubble form in blood. This cause decompression. Decompression sickness. Divers use a special gas mixture. Here, let us discuss now numerical problems. Numerical problems regarding Henry law. Henry law. Number 1. At 298 Kelvin, partial pressure of CO2 gas is 2 atm, atmospheric pressure. If kH for CO2 gas is 40 atm, find mole fraction or solubility of CO2. Answer is simple. Write equation KH to X, or X is equal to partial pressure by KH. Add the value. Partial pressure is 2 and KH is 40. Answer is 0.05. That's all. This is the answer. Let us take another question. Question number 2. If pressure is doubled, then what happens? To solubility. Write the answer in this way. P is partial pressure is directly proportional to solubility, that is mole fraction. So by doubling pressure, solubility doubled. Take one more question. This is MCQ type. If gas A has KH 20 atm and gas B KH is equal to 80 atm, which gas is more soluble? Which gas is more soluble? Answer is simple. Solubility is inversely proportional to KH at constant pressure. So what happens? Lower the value of KH, higher is solubility. Answer is gas A. Answer is gas A has higher solubility. Now I'm coming at the end of my explanation. Today we learned solubility of solid in liquid, 1 point, effect of temperature, solubility of gas in liquid, Henry law constant KH, and real life applications.